On the other hand, I did not want to lose her for the school, because to us, she is the one of the best person to give the lecture. So this compromise I have done. So she will give in this to the Zoom. Isabel, just 2 minutes. As I mentioned that we had a photography, so it's little bit delayed. Just 2 minutes.
No problem.
Okay, students. So we'll start these third lectures. And as I mentioned that these lectures will be, and tomorrow her lecture will be in Zoom. So just a small introduction to the Professor Isabel. She is a staff member of SAN since 2000, I think, since 1996. And at present, she is this main person to look for the configuration, quality, and scouting for the high energy, high luminosity LHC project. And she is involved in this many scientific activity as a researcher, quality manager, and group leader. And she is also the advisor of the SAN Director General. And her primary interest are the coordination of the large scale international technology and the science project, the involvement of the educational sectors, and also innovative industrial activities. Okay, so with that few words, I request Professor Isabel to start her talk. Isabel.
Hello to everyone. I'm really sorry not to be with you. I would have loved really to be with you in Mumbai. So you had already a short presentation of who am I. Effectively, I started in '96 testing the magnets from the AC. I passed all the first years making the installation of the AC machine, part of the Atlas infrastructure. And after I had the pleasure to work for high luminosity. So I have seen from in the beginning of the beginning with high luminosity to the moment of the start of the construction with LHC. So the full process of an accelerator that before it was taking just a few years, as you will see, now takes a full life of everyone. And even now I have a team that is working on the civil engineering of FCC. So a lot of years, only one machine, but a lot of experience that I will try to pass to you during this presentation. This presentation contains material of a lot of people. So that's why I put et al, because it will be too long to add all the persons that have contributed to the presentation. I will upload them tomorrow because it's the full set of slides from the 2 days. So I'm trying now to pass to the next slide. I hope it works. So next. So let's start from the beginning. Why we do have accelerators? Well, accelerators are discovery tools that have multiple uses. We will explore during the 2 hours that we will pass together their history, their types, their use, the technology required to build them, and finally, how they are used in high energy physics and all the new machines that we would like to build to continue the research of the fundamental building blocks of nature. And then I will also provide a very, very long bibliography, because in 2 hours we can just grasp some concepts. So I hope you are interested in learning a lot more. So there will be plenty of books and other pages where you can see really a lot of things and learn really about beam dynamics that is necessary and all the other components of an accelerator and all the other things that you will need to know if you really want to work on your field. So let's start for the history of accelerators. And maybe you are wondering why I start with that. I think because it's important to understand how things have evolved and why we have the machines that we have today. And not forget the old ones, because even if they are not used for high energy physics, they are really used every day. So why we have accelerators is because they are really great research tools. We are curious, and we have always loved understanding what is around us. So we have always created instruments to help us in this knowledge way. So we use them sometimes to trace, to observe with more precision, to recreate events, to experiment scenarios. So always experimental tools have been used to a lot and variety of things. And without doubts, even if the LIST is the more sophisticated than the Galileo telescope, each one of them in their period were really at the frontier of knowledge. And everyone that built one of them, they were pioneers. And this is a concept that we have to have also in our minds. Sometimes even our ideas cannot be developed in the moment that we are, because we were so far away that technology was not at that point. So we never have to stop an idea, even if the technology is not yet there. So, but if we now center back again to the accelerators, a lot of people ask when it all began, which was the first one. So of course, like with everything, there's a lot of different opinions. People that is more from UK, they will tell you that everything started with Rutherford, who in several of his speech to the Royal Society inspired everyone, giving them the concept that we should be able to manipulate this new nature, the reactivity, even to create it artificially. So this concept, of course, came in the mind of all his students. And so a few years after, Cockcroft and Walton prepared what it's considered the first particle accelerator, even if for me it's not, for a particle use, for the split of lithium into alpha particles. And they created the first electrostatic accelerator. At least they say that. But in reality, the other person that is there, so Van de Graaff, in 1929, he already created an electrostatic generator. And he created it not to split the lithium, but really because he wanted a particle accelerator for physics research. And he saw a great potential on it. He thought that really that accelerating particles must be the future. And in some way, it was, even if his accelerator, that was not a really accelerator because it was limited by the gradient that you could apply, was the first ones until the cyclotron, that we will see in a few moments, was invented. What happened then? So next slide. Well, that, as I said before, we don't always have to think that the one that is more famous is the real inventor. My personal opinion, and again, it's my personal opinion, and that if we have to think on a real father of the accelerators, it will be Rolf Biederoy. That is the first one in the slide. And supported by Gustav Ising, that he didn't know that he was going to be the real inventor of accelerators, but he was a theoretist. And a lot of times you will see that advancement in accelerators is this dual career, in the sense, not dual career of two persons, but always a theoretician that have the ideas and someone more practical that is able to make them in reality. In 1924, so far before, Gustav Ising proposed a time-varying fields across drive tubes as an accelerator mechanism. So he had this first concept of what will become one day a LINAC. And he had the concept and he wrote the article, but it stayed there quite a lot of time. The first accelerator really came in 28 when Bejar, that was an PhD student in a German university, even he was Norwegian. There was a lot of things happening in Germany in that moment, demonstrated that the ISIN principle could work and make the first LINAC. It was used arriving to 50 kilo electron volts, but he created the first LINAC. The funny thing is that this was not the proposal at the beginning of Bejar. This was a backup solution for Bejar. His idea, his concept was a betatron, but he didn't manage to make it. So because he had to present his thesis, he saw this article, thought that was simpler to make it reality, and he created this first LINAC. His concept of the betatron stayed calm for a long time. And it was not only until the 40s that another person, Donald Kirst, created the first betatron. That was quite a good machine in any case. But it was not Bejar, even if he was the theoretician in that case for the betatron. So the moment was bubbling, because we have seen that in the same 20s, we have from one side, the people working in electrostatic generators in both sides of the Atlantic. We have in Europe the first concept of betatrons and of LINACs, but in reality, that was not the only ones. There's other theoreticians that like Leo Szilard. His name was changed because he was Jewish, like a lot of them. And he was the first one making a patent. Yes, in that period, Einstein had a lot of work because there was a lot of patents. And he created the first concept also of linear accelerators in the 28. So again, in more or less in the parallel, there were so many things that were created. And the first cyclotron. And the cyclotrons will be the next step. Because even if he was the theoretician, even if he put a patent, the first one that we will name that is really the father, is the second one, that is Ernest Lawrence. Why? Because he was the first one putting it in practice together with Livingston, that was his PhD student in that moment. And why he was able to make it reality? Because he was really well known in his university. So he had the possibility of obtaining money to make it in reality, because again, even if the first one, it was only 11 centimeters, as you can see in the slide, he obtained the money also to continue making cyclotrons beyond this 11 centimeters model. How much energy he obtained? We still are in the range of the kilo electron volts. He managed to make this 11 centimeters machine with 80 kilo electron volts. Again, we can contest a lot of things always of who was the creator. And we have to think on how this large team of people together create so many things in so little time, and how everyone inspired everyone. Because theoretically, Lawrence was inspired by an article of Bejar. Bejar was writing in German, and Lawrence did not read German. So it was only looking at the formulas that he got inspiration. And again, one was talking about LINACs, and he created a cyclotron. So it was this moment of really bubbling of ideas and of energy. And one of the fully not knowns, people also working on accelerators and creating great machines, was the person that we don't even have a photo in the corner. This person is Jean Thibault. He was a physicist working with de Broglie. And he also considered that we have to be able to manipulate this new energy, and he thought that the first, again, using the first concept of LINAC, that he can put ions and put the same concepts of a LINAC and accelerate them. And well, he was very successful. He put 11 RF gaps. So creating this first LINAC, and he realized that the LINACs have problems. And then he built the cyclotron and the 32. So in reality, a bigger cyclotron that Lawrence had built in that moment in the States. And the problem that he was not so popular as Lawrence, so he asked for funds, but he did not obtain. So finally, all the progress of the cyclotron was really done by Lawrence. So as a message is that you can have great ideas, but you have to have also the persons that support you in the universities to make them reality. Linux are incredible machines, and if you have to think on them, think that today are still in the new machines that we will develop. Still, when they were created at the beginning, and the reason why the students of the Berkeley did not continue with it is because technically the capacity that we had to make a ref systems was not good enough in the 20s, on the beginning of the 30s. It was only in after the Second World War that we had a jump in the technology, and then we could have real Linux. And it was Luis Alvarez that created a new Linux with a different concept from the one of Bejar, but that because he had that resonance chamber when the particles were traveling around, and he had used the tubes to protect while it was accelerating. So a concept that was really different from the one of Bejar, but again, using the same ideas. And there we had a gigantic change because he was able to reach mega electron volts, some things that before was impossible with all the previous machines. The Linux have moved even further because we have continued developing the technologies.
Isabel?
And, yes?
Actually, looks like you are saturated. So can you just move your microphone a little bit?
You hear me better?
No.
Even closer? Better? You see a difference?
Okay, whatever the possible you do it. Okay. Cannot. No, subtitle, I think this link, we do not have that. This is, yeah. Okay, I think you continue.
I continue. So I have to take back where I was. So we were talking about the Linux and how important had been the changes in technology. Because again, the next real advancement in Linux was when we had superconductivity. We discovered superconductivity, and we were able to make these cavities in niobium, and then really change completely the electrical fields that we could have in a cavity. Also, the other innovation that arrived and also make a revolution in Linux was what we call the radio frequency quadrupoles. That is a new type of accelerator cavity that is able to do at the same time acceleration, but also focusing. So remember that, because it's very important. Sometimes you can have the great idea, you can have theory, a great idea, try to make it reality, but the technology is not still there. So it's very important to work with industry, to work to make things that maybe it works in the laboratory, work beyond. Because when you will build a big machine, you will need really the industry and the capacity of repeat the same object several times. So we have seen the first machines, but now let's go to the real one that really make the revolution. Why? Because all the other machines, they had limits. A cyclotron have relativistic effects. The magnets are gigantic. You don't have enough focusing. So we really needed to go to another machine. And again, it's Bejar who makes this change. And he is the one that has the first concept of circular collider and call it cyclotron. And cyclotrons are mainly all the machines that we today use for high energy physics. But the first concept, in the same way that when we are talking in the 20s and the cyclotrons are developed everywhere, the electrostatic accelerators are developed everywhere, happens the same with cyclotrons. Then there's an explosion in both sides, in UK and in the States, and after later in Python, there's all teams that gets together to create cyclotrons. And again, these energies move beyond. We are not in kilo, we are not in mega, we are going to gigas. So the first synchrotron that was created in the 46 was not yet, but in 47 already, we had the first giga-electron volt machine in Birmingham, UK, one of the photos, the one in the bottom. But they were not the only ones, because in the States, in BNL, they created the Cosmodrome that gave a lot of Nobel Prizes with only 3 giga-electron volts, but already something that was beyond the imagination of all the physicists before, and creating the possibility of putting in practice and experiment all the theories that were, again, bubbling and living there. So cyclotrons were really the first and really strong discovery machines. The number of machines that follow after these 2 first ones, it's incredible. And even if I'm going to name mainly the more important ones, it was really everywhere. So in Italy, in France, in Germany, not only at CERN in the States, but really all around in the 60s and 70s. So if we have to name, of course, we have the PS at CERN that is still on work. AGS and BNL, ESR at CERN that was dismantled, the Tevatron Fermilab, RIP, sorry for it. SPR at the SLAC, SPS again at CERN, the LEP at CERN that was dismantled one, the RIC at BNL that is still working, and of course the LISI at CERN. So synchrotrons, of course, can accelerate to much higher energies. And of course, they have limitations, mainly for electrons, because we have synchrotron radiation. Still, the energies that can be obtained are clearly superior to any of the other machines, and has a clear advantage, at least for me. And is that as we have a circle, we can have different points of interaction, and then we can have several experiments running at the same time. I think that even if I love Linux, this gives an advantage, because physicists, we all have different ideas and we all want to test. And always is nice to remember that in the SPS, there was UA1 and UA2, and both they had the possibility of discovering what was the one that was there, because they have to eliminate one to put the other. So of course, a LINAC will always have the problem of having one single point of collision and only one experiment at a time. What again, a synchrotron will have several points of collisions and then several experiments at the same time, several different characteristics measured, and the capacity also to check that everyone is observing the same thing. So we have had this overview of all these machines that we have already built. And I like to put together these 3 different curves, because are from different dates. Means that also how we have seen the evolution have changed all along, and also the construction of machines have decelerated or not accelerated. Because each time we have looked for machines that are more powerful, machines that require to reach higher energies and higher luminosities, but mainly higher energies. And so each one of them required more effort, more teams, and working together. So before a country could pay for one machine, the States can steal, or China can steal, finance one big machine. But for us, for Europe, we needed to be together. That's why CERN has so key, because the funding and finding the funding requires a lot of effort. So, and requires a lot of funding. So we cannot anymore think on these solos. So this little team that in Berkeley or in UK and in the different labs, they were able to make a machine, or in Athens in Italy, that it's probably part of the past. If we are, again, thinking on high energy physics and with accelerators, there are other type of physics and other type of research that of course can be still be done and be very interesting with machines that are far less powerful than the ones we are talking about. Now, I know that the talk is based on high energy physics, but you are working in instrumentation. And let's put that slide. I have to pass you the message that accelerators are very important and real tools for humankind. So we don't only have to think on accelerators and think that there's only 5 that are still working for high energy physics. We have to think that today, if we are thinking about accelerators, we have more than 30,000 accelerators at work today. So of course, there's more that have been produced, and there's of all types, but today there's 30,000 accelerators working every single second of the day. And beam particles are very useful for a lot of things. A beam of particles, it's used for chemo treatment, for produce energy, and on all kinds of process of creation of energy, to use for inspection of cargoes, for material science, for eliminating bacteria from drinking water, to mapping proteins, to help on the mapping of proteins and others, to design new drugs, and for material science. It's really a universe that can be explored with accelerators that goes even to art, and again to fun dating, not only dating but more, and to study nearly everything that you can imagine and more. And so you have to think them on real tools with a full diversity of usages. So an accelerator, as said can use it for environment, medicine, industry, mass spectrometry, security, and of course, discovery science. So one of their usage, of course, is energy. And they have such a potential that you have a full report that is in the bibliography that will explain to the politicians. And the way I'm explaining this is like you will explain to a politician, because you can't think on the machines. So physicists normally will explain you that we have cyclotrons, neutron explosion sources, and cyclotrons, and talk about machines. But when we talk to the public, we have to address them on which are the usage that they can have. And that sometimes we are developing for high energy physics technologies that are going little by little to go also to all these other instruments that really are there and use it every day by us. So sometimes exploring technologies for high energy physics is really useful for all the other ones, all the other accelerators that will be used in life of the people. So of course, if we think about energy usage, you have it again for transmutation. There's a lot of projects in this moment because of all the crisis of energy that have that were again more in the drawers of the people, and now have come back because we have seen all the possibility of using accelerators for transmutation from the usage in new generators with thorium. It's a real vast possibilities of use of accelerators for the production of energy and also for the elimination of nuclear waste, but also clearly for everything that is cleaning of air and water, the capacity of really eliminating bioradiation, all kind of bacteria. The other field where clearly it's key is medicine. Already in the 30s, Lawrence used his cyclotron to produce radioisotopes to be used in medical treatment. And the first Linux were used also to treat cancer. So everything that we develop, not only for machines, not only for the accelerators, but also for DuPont, really for the experiments and for the detectors, are used every single day to save lives. And of course, also the production of radioisotopes for tracking and for imagery. So it's we cannot imagine anymore medicine with the accelerators. And part of our work, even if we, for example, I remember the first team when I was really young, so at least 30 years ago. One of my colleagues that was sitting in my same office, he was working for PIMS. So the first concept of how I can make a radiotherapy center that can be copied and put everywhere in the world. And some of the ones we have in Europe are based on this PIMS study. So even if if we are normally working for making high energy physics accelerators, our concept or ideas can be used to really meet those accelerators that save lives every day. But if I have to put a field where really accelerators are every day there, is the industry. Or because we are using as electron beams or with ion beams. So ion beams are clearly key for chips manufacturing, but electron beams again are used for more biological processes, but also for material science. We have also all the big machines, the cyclotrons and the neutron sources that are used for research, for making the development again of biological components and for material science, and also use it to study how things behave if we have a strong radiation of them. So they are really key instruments. But mass spectroscopy has also made radical changes on how we see and how we investigate the atmosphere with the studies of gases and aerosols, but also the study of the seas with all the hydrosphere, where we are using again accelerators used to, and mainly the mass spectroscopy to study really what we have in the different components and how they have evolved with the time, with also for studying of the ice, the lithosphere, the cosmosphere, the technosphere. We really use it for really understanding. Do you remember my first slide of the tools and the research of the knowledge? So they are really tools that you can use every day to understand better where we live and how our world has evolved. Some politicians will also tell that can be used for security and defense. Personally, as I work for CERN, is the field that interests the less. But it's true that the wire chambers that were invented by Sharpak at CERN are used, the detectors that are used for effectively all the inspection of cargo containers since several decades. And that allows really, with little dose, be able to identify what is inside cargoes without opening them. And so easing the life and protecting us. And finally, there's a lot of other usage, but it's also used in art for avoiding to use have to cut a little piece for making a carbon-14 analysis and really see if and avoid instance, be able to understand if there's some fakes and if we can understand if the paintings were done with the same techniques and with the same materials, and even discover things that are behind what you are seeing because we're eliminated. Like you see in the bottom, this little thinking in black and white, it's what could be seen with X-rays fluorescence because it was deleted because it was written at the beginning, then deleted years after, but we still can see the iron, and then we can see what was the first original drawing inside. So all this perspective was to give you this impression of how accelerators are incredible tools that you have a lot of work in the future, because accelerators will be continually used everywhere and even expand as tools of research. And again, that they research are infinite. This is the mapping that we normally put on our team of technology transfer that indicates all the tools and all the components of an accelerator and where they are used. And as you can see, the palette is infinite and is not really limited to high energy physics. So now that we have seen this historical perspective and how they are used, let's go to how those work an accelerator. So we are going to look at the different components and how they are used. So this schema was the first one I saw in '95 when I made the US. They put me this schema and says, that is how it works in accelerator. And it looked to me quite simple because I saw only injection, collisions, bending machines, accelerator cavities. And in reality, you need a few more things. So let's work together to understand what you need in an accelerator. First, you need particles, because if you don't have particles, you cannot accelerate them. After, you have to inject them, and it's not so trivial in reality. After, you need to be able to make a track, because particles must go following a trajectory. So you need to make a track that is clean so that they can circulate without others colliding with them and taking them out of the place. You need also to bend them, because if we are in this case in a synchrotron, you need to make them follow the curvature. You need also to focus them. Remember when we were talking about the cyclotrons, if you are not able to compact them enough, when there will be the moment of the collision, they will not find each other. So we have also to focus them. Of course, we have to accelerate them, because if not, we will have just particles inside, but nothing happening. And we have also to eliminate those that are not in the good trajectory, so the ones that are not behaving as you will expect. After, you need to observe them, because if you cannot see what is happening, probably you will not find when things don't work, and you must really to be sure that everything goes as you expect. And after, you have also to extract them, sometimes because you are putting them in a fixed target, or others because you really have a problem. In our case of our magnets, you have a quench, and then you have to extract very quickly, or you simply because you have burned the most part of the particles and you want to really eliminate them and sending it to not a target for making physics, but you really to dump all the beam. You will also need a lot of more components, because all these things need energy. In the case of cryogenics, if you have superconducting devices, so you will need all other components that will go around, from civil engineering, from cooling ventilation, electrical distribution, so an infinity of other things that go together. So let's try to see them one after the other. But I will name to Lynn Evans and Emilio Picasso. Both, even if the one was in LEPAN and the one in LIPSI, say the same thing. Accelerator physicists, normally they focus on the components I have shown there, but the place where we always have our cost is always on the things that are not in this diagram. So it's on this cryogenics, electrical distribution, cooling and ventilation, and civil engineering. So don't forget them, because depending on how you have made this machine, they will cost more or less. So all the design have to really be integrated and work together. So we were talking about how to get the particles. Normally, you will use a dual plasma transfers. So a way of, in the case of us, to take hydrogen, take the electrons, get only the protons, and have this first acceleration. Now, of course, with just this simple device, you reach 1.4% of the speed of the light. But you will need, depending on which are the energies where you have to arrive, you will need a complex system of accelerators that will go one after the other, accelerating more and more, because you will have a lot of limits that if you look at my reference and you go to the part of beam dynamics, you will understand why you need this complex system of getting to certain energies and moving to another system that can eliminate some of the problems of energy that you will have. And you will, if you look at all the reference, you will understand what I mean. You will not also need a system of injection, of course, after extraction, as I have said, to eliminate the beam. But that is also a very complicated system, because you need in some way to kick these particles inside the beam in the right moment, and you will have to again kick so that they follow the right orbit after. So we have a lot of systems of magnets that will deviate the orbit, and after others that will really give the energy to correct the orbit. And again, it's one of the always forgotten items in an accelerator. Everybody thinks on how you make the particles run, but not how you inject them and how you make them get in the right moment. As I said, after you need a track, and this is ultra vacuum. One of the real key elements, in a sense, the most part of, if we always have, we have been also so proud at CERN of having such a good accelerators with such a luminosity. I think one of the key concepts have always has been that we have a real great vacuum and a great vacuum specialist. Because of course, if you don't have a clean track, so if you have all kind of particles that still are in your vacuum tube, they will collide and make interferences. And also because the beam tube is not only the track, it's also the first place to protect your other devices, in the sense that our beam tubes will have, in some cases, beam screens and all types of things to protect whatever particle that gets out of the beam to destroy the superconductivity of our magnets, for example. Because it's true, we are normally thinking only on the normal track, but when we are arriving to the experiments, we have to really collide far more the particles, and then there's also a lot of particles we have to eliminate, and they will go to our magnets. So it's a complex system that is really fundamental for you. And this image was one of my colleagues that prepared of which is the pumping volume that you have to eliminate, gives you really this impression of how much effort has to be done. And again, don't forget, it is not only the coating that you have to do, the pumping that you have to do, and all the technical infrastructures that have to go with it so that it works. And when we think about, again, vacuum, you have to think on all the flexible things that have to go around. We are, in the most part of the cases, talking about cryogenic machines, so that have all the contractions that you can imagine and all the movements while it's contracting with when it's getting cold. So, and we have to use also technologies in all the junctions, because of course you have to consider all the relative movements. So it's not so obvious, and it's a full science. And again, if you want to know more, there's wonderful books specialized on the Sun Accelerator School only on vacuum. And the kinks, the magnet system is, for hadron machines, considered the king of the systems. In the same way, the RF cavities are considered as the queens or the kings of the electron machines. We have magnets for everything. Of course, dipoles for bending, quadrupoles for focusing, sextupoles for chromaticity, octupoles for tune and amplitude, but also we have decapoles, decapoles. And if you think at CERN and DLSD, a lot of them are not even powered, because what you need is a complex system that allows you to really get the beam where you want it to be. And when I remember when I was very young and we were testing the magnets, one of my work was used to make the mapping of magnetic mapping of the magnets. And you always think that a dipole is a dipole, but in reality, on the paper, a dipole is always a dipole. But in the reality, when it's manufactured, together with the dipole, you always have quadrupole and sextupole and octupole and decapole components. So all the other magnets will also correct. And for the fun, the magnets were classified with colors. So you have gold, and you have all kind of colors that were telling you how much pure there was this dipole and how they were able to be flexible and put in the very special places because they were as pure as possible. But of course, a lot of these other magnets are correct the problems that are normal. So it's again, this touch of reality of how things are really are when they are built. But all these magnets also are going to be positioned in a special place. All the quadrupoles will be, as I said, also used for compacting and for maintaining in orbit all the particles. So they will have this effect of photo lenses that will allow you to maintain your bunch of particles in the right place. The ref cavities are, as I said, the queens or the kings of the electron machines. Of course, when you are in hadron machines, you need them, because if you don't have them, you will not accelerate, clearly. But you are not losing so much radiation in synchrotron radiation. So of course, you need to feed continuously in energy. So clearly, when the lab was built, when still we didn't have superconducting radiation cavities, the machine was I will not say a full RF system, but it was really the key component. Today, if you think on the LEC, it's just a small section. That's because again, we don't need to once it's reached the energy, we are not losing so much during the runs. But RF cavities is again a full wall with all kind of cavities. And when we are talking about cavities, it's true, we are always thinking on those, the ones that accelerate, but that come from high luminosity. We are using another ones that are cavities that are completely different and are used for compacting and kicking the branch. So you have to think also that it's a full wall, and that the discovery of superconductivity have made it evolve completely. So we have seen how we can have a track, how we can vent the particles, how we can concentrate, how we can accelerate. So now we have also to have systems to eliminate the bad boys and the bad girls. So the ones that goes out of the orbit. And for that, we have a very complex system. I will say it's complex because it's really complex system of collimation with all kind of collimators with different nature. They are going to be established in different zones of the accelerator and to eliminate what we call primary and secondary collimation, because you are going to eliminate different particles and you will combine them so that really your beam is as clean as possible. And the type of machines that we have are completely different and is in complete exploration. In high luminosity, for example, we have really explored all kinds of materials, because sometimes we have problems because the materials are not able to resist the power of the beam. And then we have pollutions, and that makes that we have again to clean the machine and to restart. So really is and again, a very important component. So not to forget it in any of your designs. We have seen components, and now we go for instrumentation, because the eyes of the machine are the instrumentation, the beam instrumentation. And I have just put a few of them. They are infinite number. So in using high lumi, we have 10 different instruments that we put in the beam, used to know how it's behaving and how we can really improve. In the period of the LEP machine, so the first electron-positron machine that we have before the LHC, everybody said that was so difficult to tune it because they have little instrumentation. And now you see the beam, you know everything that is happening. And of course, there's a lot of statistics, so you don't see the beam. But it's what allows the high performance that we have in the machines. That is an example of a BPM, but again, I could put, if Rodri will be here, he will put 25 slides only and explain you with a lot of passion how instrumentation, not only for the experiment, but also for the machine, changes us completely the life. I had said also that one important point is cryogenics. As we are always working with superconducting machines, because it's the only way to have the energy that and the magnetic fields that we need, implies cryogenics. If we think on high lumi, I don't say that cryogenics have cost as much as 1 kilometer of tunnel and galleries, but yeah, more or less. So it's a very important component in the way that you have designed your machine. Will imply how much you are going to cost. The cryogenics will imply how much it's going to cost. And the thing that when you have to design is you have to design also to be able to take out the helium and to put it back again and absorb all the cycles of cooling and that you will have. So again, your design will change completely how your installation of cryogenics will be. And finally, powering, storing energy, and eliminating energy. These are key elements. When we have a quench, all the energy in the machine is evacuated in a few nanoseconds. So if you don't have a system that will capture this fresh energy, if you have a system that is going to heat up so that there's a good gradient inside your magnets, you will destroy them. And everybody remembers, even if it was not a quench, what happened in the LEC machine the 9 days after we put it up. So you don't want to really have a discharge of all the energy of the machine, and because then you will know that you will have 2 years, at least for us, 2 years of shutdown and a lot of effort to repair all your accelerator. So those are really also key. And finally, finish with the part of components of the machine, think on the technology. There is a cable of neobium-titan that is the one that we are using in the magnets. It's really robust. If I think in high luminosity where neobium-13, it's not as robust as neobium-titan. So things that you can do, margins that you can have in the industry with some components and some materials are impossible with other materials. Some can be industrialized, something are really difficult to be industrialized. So have this in mind always in your design. Of course, I'm talking about accelerators, but whatever you are designing, whatever instrument you are designing, think if can go to industry. Think if the industry will be ready to produce it, and if they will be able to, and ready to produce them only if they can do it more than once. Rarely, unless it's a small, medium enterprise, will launch themselves in a big production unless they know that they can reuse it back again. So this I will jump. So let's go to the final part of the presentation, a wall of colliders. Now let's go more close to high energy physics. I have just given you this full impression of what are the history, the usage, the components. So what are the wall colliders that we have today? And you think of the graphs that we had, and you think what are the ones that are really used for high energy physics. And again, it's for high energy physics. We have a lot of synchrotron light accelerators, we have spallation sources, we have all the things. But here are the ones really working on high energy physics. They're every time less. Because again, complicated machines. Still, we are all the time talking about new ones. And if I want to make a little joke, it's because they pay off. So in the history of the novels of physics, this was from 2010, so the one is for the Higgs.
Isabel,
yes.
Can you finish in 5 minutes your time? So, and yeah. 5-minute questions.
So I will probably take 7 because I started later. Now, more than 25 Nobel Prizes were won with accelerators, so that it's normal that we continue thinking them as the key machines for discovery. And if I look at all this avalanche of machines that we have had, they have been really key for all these Nobel Prizes and for all those discoveries. But each one of them needs more energy, and each time are more complicated. And what's more, they need to be together. So you cannot create really new centers because the most part of them, they are fit one to the other. And so you cannot really, if you have to see things as a completely new machine in a new place, it will be impossible because all the other costs that are required to inject the particles, to maintain them, and all the infrastructures, if they are not there, you will have to pay them by yourself. So that makes that it's not so easy to make such a complicated machines relatively easy. It's not only the numbers that you have had. We are thinking about machines of 27 kilometers. If I think in the future, we are talking about 190 kilometers. So in the meantime, we are thinking also on how to improve the ones we have. And we are talking all the time about energy, but the other factors that can be improved is luminosity. And if I think on the performance of the AC, we will say that it's great. If you think on the curves that you have here in the bottom, you see that every time we're able in less time of producing more luminosity. After the last stop we had, where we have an incredible increase on luminosity on the injection chain, so the PS, SPS, and all the machines that are injected into the AC, we have seen, if you look at the 2022, you will see that in just a few months, we have done nearly as much as we have done in all the other years. So luminosity is also key for having more collisions and then more statistics, and so for more refining and more physics. But in reality, we cannot continue like that. And I'm approaching the last slide for today. So why? Because as I said before, when you're designing a machine, one thing is how you design it on paper, and the other one is the things that you can really produce in reality. And so when we make the LAC, unfortunately, some of the components were not designed to receive as much radiation as they will receive in the future. So LEC, if we don't have high luminosity, will stop in a few years. The calculation is probably in 2027, 29. It's the maximum, really, really the maximum. After we will start having really breaks or injections, since all the quadruples that we have in the insertion regions, they will break one after the other, and we don't have spares. So that means that, yes, as we have to change this in any case, let's change them and improve the luminosity so that we can really have a physics program that goes beyond the rupture of these quadruples in the adjacent regions, and we can go until 2041. So that's why in tomorrow, I will talk about the future, and I will talk about high luminosity and how a machine, even if we know that it's going to break in a few years, can be improved, not only because we are repairing the components that we know are going to fail, but also improve the luminosity so that we have, again, 12 more years of physics and interest in physics. So remember that you have to always build a machine that is able to be renovated, improved, and not die at the end of the original life. Think on the PS 59, is still working. Now we have changed nearly every component that is inside. SPS, the same. In the 70s, still working. So always think, also for your instrumentation, things that can be built, can be repaired, can be upgraded. So that is the part I wanted to explain you today. Tomorrow, we will really look at the future. We will look at how strategies are decided, what are the things that we are doing today, which are the accelerators that we are thinking in the future, and some of the keys on how you decide which kind of machine will really be the future machine or not. I hope it was not too painful having me on Zoom. But I'm going to end now the slides. Stop share.
Okay, thank you.
And I think that there's no time for questions, but if you have questions, you can think they can give you my email and I will answer whatever you need.
Yeah, certainly. But any prompt question now you people have?
If you are too shy, again, you can write me any moment. I know that I will not be there for lunch so that you can ask me questions. So don't hesitate. I will answer whatever I know, or I will guide you to the right person if I'm not able to answer you. But don't hesitate.
Okay, thank you very much for your nice presentation. I have a question related to synchrotron radiation. You talked about that, and how was the research going on, and what are the future opportunity related to synchrotron radiation?
So I have real difficulties to hire you. So it's not I'm not sure if I have understood your question. So you have asked about synchrotron radiation, but I have missed the other part of the question. So your question is how it's produced and how you compensate. The voice is really, I hope it was not so bad when I talk, because I cannot hear you.
Okay. Okay. Thank you very much.
Okay, then, Isabel, thank you. And
So
again,
you can write me, because the sound is really, I cannot hear you. So if you write me, I will answer you. Okay?
they will send the email to you and they will get the reply. Yeah, okay, then thank you. And again, see you tomorrow.
See you. Bye-bye.
Bye.